Testing. Okay, folks. Data 8, lecture number 22. Announcements. There was lab, but there was no lab notebook this week. Oh, there's a midterm tonight. It's good to try to arrive at 7 if you can. We'll start handing stuff out, make sure everybody's in their seat, but we won't actually start the exam till 7:10. So if you have a class that ends right at 7, you can just like scurry over to your exam location. And if you get there by 7:10, you won't miss the exam. The exam lasts for 110 minutes, which is not quite 2 hours. That's an hour and 50 minutes so that you get out by 9 p.m. That's the goal. Hopefully we'll start on time. We will give you the midterm reference sheet and the exam itself. You got to provide pencils, erasers, and bring your ID. Questions? Yeah. You can use a pen. If you like to live dangerously, you can use a pen. Okay, last lecture, we spent a lot of time discussing the following question. Let's say the manufacturers of super soda run a taste test. 91 out of 200 tasters prefer super soda over its rival, and we assume that these 200 taste tests were a simple random sample from the population of people that we try to sell soda to. And the question was, in that population of people, do fewer people prefer super soda than its rival? Or was it just by chance that 91 happened to come out, even though it could have come out, 110 or 100 or whatever? We came up with the following null hypothesis together, that half the people in the population prefer super soda. So if you take a super simple random sample of 200, you'll get some people who like super soda and some people don't. The alternative hypothesis was that fewer people in the population prefer super soda than its rival. And as a test statistic, we found out that there were many options, but the simplest one we could think of together was just the number of people in the sample who prefer super soda. The observed test statistic was 91. We also sampled under the null hypothesis many times to get many simulated test statistics, and we looked at their distribution. When we looked at their distribution, we were able to calculate a p-value, which we got by looking at the distribution under the null hypothesis, finding the observed test statistic, and looking left. Why did we look left? That was in the direction of the alternative hypothesis, where we thought that fewer people in the population prefer super soda than its rival. So 91 or fewer. We then calculated the p-value as the percentage of the simulations where the test statistic happened to come out 91 or smaller. And we found that was 11%. 11% was not below our p-value cutoff of 5%. So we decided that we could not reject the null hypothesis. The null hypothesis still looked pretty good. There were some questions at the end, and we didn't get through them all, which is why I'm bringing this up again. What affects the outcome of a hypothesis? Well, let's kind of go through it. The hypothesis you investigate can matter. Like, you pick the null distribution, and so you're going to decide what simulation to run, and that will affect the outcome. The test statistic you choose can matter. If instead of having the number of people, we just tested was the number less than 100 or not, we might have gotten a different answer. How many times we run the simulation under the null distribution can affect the p-value that you get at the end. Whoa. Let's watch that happen. Okay, so from last time, hopefully you watched last time's lecture. We actually ran one taste test with 200 people. 91 of them liked super soda. But then we decided that we could simulate under our null hypothesis how many people would like super soda if we asked 200 people, that's our sample size, in a world where preference between super soda and its rival was like a random coin flip. And heads meant you like super soda. So running this once gave us the number of people who prefer super soda out of 200 in a randomly simulated version of the world under the null hypothesis. And this varied a lot. So we ran it 10,000 times and got a distribution under the null hypothesis of the test statistic. And we found that it was usually around 100, but it wasn't so uncommon that it was 91 or less. In fact, the fraction that were 91 or less was 11%, which is kind of small, but is not so small that we could reject the null hypothesis. We were looking for like 5% or less, and that's not what we got. Okay, what if we had simulated using fewer simulations? Like instead of 10,000, what if we had only done 100? We're going to keep the data fixed. We're going to rerun the test, but we're going to try a different number of simulations where this could be 10,000 and we have 200 people that we sample each time. The code says, now we just run for the number of simulations and append the count that we observe in that simulation just like before. So this is exactly the same code as I had before, except now we're generalizing over the number of simulations, and then we're going to run that test and compute a p-value. So if I do it once, I got 11.62. I do it again, I get 11.13, a different answer. I run it again, 11.17, 11.84, 11.55, 11.55, 11.47. If I run this a bunch of times, oh, I saw 12, but everything's right around 11.5. The reason that the p-value is not changing much, even though I'm running these random simulations, is that the data are the same. Everything I know about the world is the same. The only thing I'm changing here is the random simulation under the null when I'm flipping coins to pretend I'm selecting people from a population that's 50 super soda lovers, 50% rival lovers. That's changing. But since we're simulating 10,000 times, it doesn't change very much. But look what happens if I don't simulate 10,000 times. If I only simulate 100 times, what kind of p-values do I get now? Are they always 11.5? No, that one's 10. Would it help if I multiplied this by 100 just so you can like see a percentage? Okay, so the old version was giving me numbers like 11.5 or 11.2, 11.3, 11.4. Here, when we simulate only 100 times, we get 11 or 7 or 10 or 10 or 8 or 11 or 12 or 12 or 17 or 9 or 12. These are all over the place. They're all kind of low. They're all below 15. There's even, if we run it long enough, probably a case where if our p-value cutoff is 5%, we might even get a number lower than 5%. Okay, not very often. Oh, there it is. Okay, so we could reject the null in this case. So we had to like try it a bunch of times. But what we saw here is that by running our simulation a small number of times, we saw much more variability in the p-value that we computed. In fact, if we try 100 and 1,000 and 10,000, and we try each of those 50 times so that we can see the kinds of values that we get out, and then we draw a histogram for those, you can ignore the code. But what I'm doing is basically running this cell 50 times where I'm changing this to 100, 50 times, and then 50 times with this is 1,000, and then 50 times with this is 10,000, just to see what kind of p-values I get out with the same data. It turns out that by simulating 10,000 times, we always get a p-value that's right around 11%. But if you're simulating only 100 times, that's in the dark blue, we get p-values all over the place, everywhere from 5% to 20%. So the importance of a large number of simulations is to make sure that you have a stable p-value when you run your simulations. So you pick a big number. Okay, 2 people nodded and everyone else stared at me like I'm crazy. So questions? We're okay? Yeah. Is this the law of averages in action? Yeah, absolutely. What's going on here is that every time you run a simulation, you're building up an empirical representation of the distribution under the null. That distribution under the null, if you only have 100 simulations, is really bumpy. In fact, what I did here is I just ran it twice. 100 simulations for the first experiment, and then 100 simulations for the second experiment. And these histograms are supposed to approximate the null distribution. But they do kind of a lousy job in this case because they're so bumpy, whereas the true null distribution is much smoother. But if instead I use 10,000 simulations, I get an approximation to the null distribution that looks more smooth. It's like better approximation according to the law of averages. And as a result, if I run it twice, I get basically the same picture both times. Now, the only thing I'm doing with this distribution is looking for the area that's to the left of 91. But getting the whole shape right helps me get a better estimate for the area to the left of 91 under the theoretical distribution. And if I did it like 100,000 times, I get an even better picture. Yeah.
It's like the more simulations you run, or the higher number that is that be more accurate, or is it like the kind of cap or more like reversal to that?
So the question is, the more simulations you run, the better you're going to approximate the true null distribution. That's right. It's just like a matter of how long you're willing to wait. So to always pick a big number.
Why are we running these simulations instead of using some mathematical, like theoretical distribution then to calculate the p-value?
Okay, so the question is, why would we ever run a simulation when we could use mathematics in order to calculate the p-value exactly under the null distribution? There are 2 reasons, neither of which apply in this particular example. One is that, well, one of them does apply in this example. One is that you can actually see what's going on. Like a lot of students have in the past statistics classes have gotten lost in the leap from what are we trying to do in the hypothesis test simulation versus how do we calculate the p-value. We're trying to make it as explicit as possible. Just by running the simulation, you can see what comes out. But the second and more important reason is that this approach is entirely flexible. Regardless of what test statistic you choose, regardless of what null hypothesis you state, you can usually run a simulation. And the way using mathematics to like compute it exactly tends to be fairly limited. There's only so many null distributions that you can do that for. So in practice, in lots of like real world hypothesis testing, people are using simulation because they want to get their null hypothesis just right, their test statistic just right, and they don't want to be constrained by what they're able to calculate theoretically. Okay. I'm only halfway through this slide. The other thing that can happen is the data you collect can affect the outcome of a hypothesis test. You took a random sample from the population, but that random sample might have been weird. That's how it is with random sampling. So you just have to be aware. And like all of this work that we're doing to like set up null hypotheses and reject them is basically to take into account the fact that when all you have is a random sample and you can't observe the population, you never know for sure. So it might be that you just got a bad sample. What do you do with that? Well, you could gather more data. The other thing that can affect the outcome of the hypothesis test is the truth. If the alternative hypothesis is true, fewer people really do like super soda than its rival. How many fewer matters a lot about whether you're going to be able to detect the difference. There's like 10 million people you're trying to market to, and 49.5% of them prefer super soda and 50.5% of them prefer the rival. It's going to be awfully hard to tell just from 200 examples that difference exists in the world. Whereas if everybody tastes super soda and spits it out because it's terrible, you're probably going to notice. We can simulate that as well. And then we'll actually do some review. But I just wanted to finish this up. Okay. Let's say that we live in the world where actually people don't like super soda. Well, 45% of them do. And 55% like the rival. So the true distribution looks like this. 45% of people like super soda, 55% like the rival. What would happen in this world? If we ask 200 people, maybe 93 of them like super soda. Not so different from our random simulation of a world in which half the people liked super soda. So this distribution isn't very far from 50-50. And so if you only ask 200 people, oh, sometimes you get a big difference, 80-20. But sometimes you get almost the same number of people liking super soda as the rival. Even though there is a difference in the population, it can be hard to tell. So here's what we're going to do this time. We're going to pretend we know the world. We live in a world where the truth is that 45% of the people like super soda. Now, if we knew this, there's no reason to run a hypothesis test. If you know what's going on in the population, what's the point of sampling? There's no point. Just look at the population. But let's just see what would happen if this were the world. 45% of people like super soda. We went through and collected data many times, and for each data collection that we performed, we ran a hypothesis test and returned a p-value that told us whether or not we could reject the null hypothesis that the preference in the population was even. So we went through and ran a whole hypothesis test after collecting new data, and this time we ended up with a p-value that was really small, so we could reject the null hypothesis. But if we did it again, collecting other data, well, 3% small, that's good. We could reject the null hypothesis again. Oh, but this time, the p-value came out at 9%, which is not that small. So we would have been unable to reject the null hypothesis, even though it was false. We just didn't have enough evidence to know that it was false. So let's see if we tried running this scenario over and over again, where each time we ask 200 people from a population that is biased, 45-55. We ask 200 people from there who were sampled at random, do you like this stuff? And then, based on that sample, we tried to figure out whether we could tell that the null hypothesis is false, the alternative is true. Using hypothesis testing, well, the only times we could tell is when we can reject the null, meaning we got a p-value less than or equal to 0.05, which did happen sometimes. Sometimes we got a p-value really close to 0, but there are other times where we got a p-value that was much larger, meaning we couldn't tell whether there was a difference or not. So when the true proportion is only 45% in the population, then there's lots of cases where you can tell the difference, and there's lots of cases where you can't. Whereas if the population were very skewed, like only a quarter of the people in the population like super soda, because it really is worse, then all your p-values end up right around 0. Like you can tell every time. So that's what I mean by, if the alternative hypothesis is true, but the difference between it and the null hypothesis is very small, then it can be hard to tell the difference using a sample. Whereas if the alternative hypothesis is true and it's really extremely true, like people really don't like this soda, then this approach will tell you reliably. show you one more thing. We're back in the world where sometimes you can tell and sometimes you can't. Because the ones where it's less than 5% is down here, and the ones where it's greater than 5% is over here. So there's some of both. What if we just had a bigger sample size? Would that help us tell the difference? And the answer is yes. So with a larger sample size, if instead of asking 200 people, we ask 2,000 people, then we get p-values that are around 0. Always less than 1%. So the way in which you conduct your experiment, it basically goes like this. The larger your sample, the more you're able to distinguish between two hypotheses that are sort of close together. Yeah. So the question is, like, can you compare a sample of 200 to a sample of 2,000? When you collect data, you're sampling, right? And when you sample by collecting data, you actually have to go out in the world and ask people and give them soda. And that gives you the number of people that you sampled, which could be 200 or it could be 2,000, depending on your marketing budget, right? Once you have that sample size, you want to keep it constant when you run your hypothesis test. So your simulations are always the same as the actual observed data in terms of the size. Okay. The number of simulations, what's the effect? Make it as large as possible. So the empirical distribution of the test statistic under the null is very similar to the theoretical distribution. You don't need to collect new data. You just need to wait, and computers are fast. So make your number of simulations large. The number of observations, here's the trade-off. A larger sample leads you to reject the null more reliably if the alternative is true, but a larger sample typically costs more money, so you got to decide how much money you're willing to spend. Larger samples are better. And what about the difference from the null? If the null hypothesis is false, but the truth is very similar to the null hypothesis, then even a large sample might not give you enough evidence to reject the null. It's just hard to tell between two views of the world that are almost the same. Okay. Let's do some review. I promised you some review. You want to review tables? You want to go? Let's do a little. Let me do a little bit. What happened? You're like, I already have to go to lecture tonight. I mean, to exam tonight. I want to do more exam, but we're going to do a little bit more exam. So if you have a question like this, which I think is shown up on every Data 8 midterm for all time, make sure you keep track of what columns there are and what kinds of values they contain. And then you're in the position of computing some value. Do it in steps. The total salary amount paid to all faculty for a table that describes one row per faculty member is going to have to sum up a column of the salary. So even though this says paid to all faculty, you just know the table is all faculty, at which point you don't need to select out the faculty members. You know you have all the faculty, so you can use the whole table. Now we use column in order to get ourselves from a table to an array, because you can't sum a table. You can only sum an array. In order to pick out the column, you can use its position, 0, 1, 2, 3, or you can use its label. But if you use its label, you have to put it in quotes, otherwise it won't work. Okay. What if you want the name of the third highest paid faculty member? Assume no two faculty members have the same salary. I'm letting you think. Okay. 20 seconds. Talk to the person next to you. See if you can make a plan. Okay. We're flying through this exam. You want to focus on their salary, right? Their salary is really important. But the value you want at the end is not a salary, it's a name. So the value you want at the end is the name of a person. Once you're down to a column of names, which is an array, you have to know the position in that column where the value you want lies. Third highest paid, well, if we found a table where the highest paid person was at the top, index 0, then the third highest paid person would be index 2. But how do we get there? Anytime you want to find the value in one column based on an order in another column, it's time to sort the whole table. Sorting the whole tables allows you to focus on one column to get the order, but then look in another column to get the value that you want. Here, you say which column you want to sort by. In this case, we also have to define the order, because by default, sorting gives you the smallest to the largest. But now we want the largest to the smallest. Nice work, folks. Questions? Huh? It is true that you don't need this word descending. You could just write true and it would work. But it's hard to know what this true is doing. So people typically write it that way just to like say everyone who reads their code knows what's going on. Huh? This I think was for real data, yeah. Usually when we write exams, we go find like real data in the world and put it on the test. You can look up faculty salaries on the internet because it's a public university and it gets really awkward, so don't do it. Okay. The number of lecturers in the department that has the most lecturers. One department has more than the rest. The department that has the most lecturers, when there are many rows with the same department, is an indication that it's time to group. When you group, you'll end up with one row per unique value of department and a column with that department as well as a column with its count, which sounds pretty useful because we want a number of lecturers, which is a count. Now, lecturers is the tricky part. Not everybody here is a lecturer. Some people are associate professors or whatever. So we'd have to go through and find only the rows in the original table where the role is lecturer. Now I have a new table of only lecturers, but I still know the department name, role, and salary for each lecturer, which gives me an opportunity to group by what? Department. Why didn't I group first and where later? After you group, you can't tell what people's roles are. So the only way to get this result is to where a table when you still knew what the roles were. Once you group, you've lost track of everything except for which department you're talking about and the count of the rows that had that department. So you have to do it in this order. Yeah. Good question. Is there another way to write this, which is r dot equal to? Yeah, that's totally fine. Maybe it's even better. Writing a value there is kind of just shorthand for r equal to. And remember that there's lots of other R's that you can perform, like above and below. If you look at your reference sheet, they're on there. Okay, yeah. Good question. Do you want to get item 0? What you get here when you group is a table with 1 row per department, and it's ordered alphabetically according to the department. So if you wanted to find the count for the department with the most lecturers, one way would be to sort the whole table and then look in the top row. But it doesn't seem like I can do that here. But another way is to get all the counts and then find the largest one. Okay. We got 30 points out of 100 already. Let's do some more. Generating random samples has 3 different approaches, and you don't know which one you're going to have to use, so you better be aware of them all. np.random.choice takes an array of outcomes and chooses outcomes from this array with equal probability for each outcome with replacement sample size times. We used this in the previous example to say heads or tails is our array. np.random choice gave us flips of a coin, 200 flips of a coin. But this one only works if the outcomes have equal probability, like rolling a fair die, flipping a fair coin, that kind of thing. Huh? np.random.choice always samples with replacement. Nope. Okay. If you have a table and you want some of the rows, then you can sample with replacement. You can sample without replacement. And if you leave out the sample size, then what happens? You sample a number of rows equal to the number of rows in the table. With replacement equals false means you're guaranteed to get all the rows exactly once, which is exactly what you want in a permutation test. You want a table with all the rows that you had before. So what are you sampling? Well, you're sampling the order. Because you're choosing row 5 first, and then row 12, and then row 3, and that's how you build up your new table. Okay, you also need to be able to sample from a categorical distribution using the sample proportions function. So if every outcome has equal probability, np.random.choice is fine. But if outcomes have different probability, then you write down the population distribution as an array, and then write down your sample size, and what you get back is an array of proportions. So handy. So want to read one thing between now and the exam, maybe sample proportions and how it works is a good thing to know. If you ever want to estimate some value through simulation, you define a function that returns one simulated value, make an empty collection array, run a for loop that just says how many times you want to run the simulation, call your function, and append the results to the collection array. We've done this in a bunch of different times, so I won't go through another example, but this exists in hypothesis testing. It also exists just in a case where you want to estimate the probability of something, like what's the chance that when you roll a die, you get either a 3 or a 4. You could write a function that tells you in one roll of a die whether you got a 3 or a 4. You could call it a bunch of times and figure out what fraction of the time it came out true. Histograms. I think you're all going to get the histogram points because we're going to practice right now. Here's a histogram. Which bin has more people in it? Notice the y-axis. Percent per $1 million. This is a density scale. It's not a number of people. It's a percent per $1 million. And income expressed in $1 million is on the x-axis. In the density scale, the number of people in a bin depends on two things: the number of people in the population and the area of the bin. So which bin has more people is another way of asking which bin has more area. Which one has more area? 10 to 15 or 15 to 25? I think it takes more ink to draw this one than to draw this one. It has more area. We can compute the areas of both. Do that. Oh, come on. This is gonna be really janky because I didn't bring my iPad. How long is that? 10? How long is that? 4? What's the area? 40? What's the area of this? 5 times 5 is 25, is a smaller number. This one has more people. We don't even need to know how many people there are in total. We just know that 40% of something is bigger than 25% of something. What percent of incomes are in 15 to 25? 40%. If you draw one bar in a histogram, okay, if you draw one bar over 10 to 25, so what if we had redrawn this histogram so that there's one bar? It's like, I don't know how high it is, but it's like one bar instead of the 2 bars. How tall will it be? Well, this one bar has to represent what percent of the whole population? 25 plus 40 is 65%. If the bar has 15 width and it's supposed to have an area of 65%, then its height is 65 divided by its width is 4 1/3, which is right about here. Okay, so I drew it wrong. It should go from here. That will be our bar right there. What percent makes 75 million or more? You do not know the distribution within a bar. It could be the case that everybody in this bar is making 85 million, or everybody in this bar is making 25 million. So the width of this thing, which is 60, and the height, which looks like about 1/5, means that maybe 12% of all people are in the bar, but you just don't know. What percent are making 75 million or more? It could be as high as 12% or as low as 0%. I want to make these janky diagrams disappear, unless you have questions. Can you get those histogram questions right? Okay, question.
So what would you want us to write?
So if this question came up, what percent makes 75 million or more? And there was an answer that said, you can't tell, you should write, you can't tell. If there was an answer that said somewhere between 0% and 12%, that's also true, but you just don't know what the exact value is. Huh? Great question. How did we approach C, even though we don't know the total population? We did know the total percent in the range 10 to 25 by adding up the 2 bars to get to 65%. And we knew that the area of this new bar was supposed to be 65%, and we knew its width. just by looking at 10 to 25. So that's how we got there. Cool. Apparently we got it right. What should we do next? You'll be asked some probability problems. What's the chance of, whatever. Here's the approach, and it works. So don't forget the approach. If there's multiple different steps in the event, like you're flipping a coin and then rolling a die based on the outcome of the coin, first ask yourself, do I know the outcome of the first trial? So, let's say we're rolling dice, and the event is everything came out a 6. You know the first trial had to be a 6 for everything to come out a 6. So if there's a clear answer for what happens first, whose probability you know, you can continue the process with the multiplication rule. Multiply in the chance of that first thing happening, and then multiply in the chance of the second trial. If there's no clear answer, like if it's the chance of the sum being 10 when you roll a die twice, you don't know what the first roll was. Could have been 4, could have been 5, could have been 6. You want to list out all the distinct ways your event could occur and add up their chances. And if it turns out that this list is really long, then look at the complement, which means you take 1 minus the probability of something else. Sometimes that complement is simpler. The most common thing I've seen in this course is the complement of at least one thing happening is that none of those things happened. You can find its chance and subtract that from 1. Okay, so this strategy is going to get us through the following problem. You put 10 marbles in a bag, 4 are green, 6 are red. You draw 3 at random with replacement. What's the probability that they're all green? Do we know what has to happen with the first one? Yes, it must be green. So we're going to use the multiplication rule. Probability that when you draw 3 at random, they're all red. Same thing. Probability that they're all the same color. Uh-oh. The first one could be red or it could be green. I can't just use the multiplication rule. Instead, I have to list out all the ways this could work and add up their probabilities. The possibilities are green, 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 or red, red, red. So I could probably compute the probability of those two things and add them together. Probability that drawing 3 at random with replacement, I get at least 1 green marble. Does the first one have to be green? No, because the second one could be. Oh, but it could be green. If you get green first, or if you don't get green first, in both cases, you could get it right. And then if you got green first, it's okay for the next one to be red. And if you didn't get green first, well, it's actually okay for the next one to be red too. It got complicated. Maybe we could use the complement rule on this one. So here's what you do on the exam. The chance that they're all green is the chance that the first one's green times the chance that the second one's green given the first one's green, chance that the third one's green given the first two are green is 4/10 to the third power. The chance that they're all red, similar structure. The chance that they're all the same color is the sum of the chance that they're all green and the chance that they're all red, because we just wrote out the two different ways that they can be all the same color. And the chance that at least one is green is the chance that is 1 minus the chance that none of them are green. And how do we get the chance that none of them are green? Well, there's only one scenario in which none of them are green, which is that they're all red. So the strategy on the previous slide is what I applied to solve these problems. These problems are like quite typical of a Data 8 midterm. We're cranking through material. Home stretch. P-values. We've used all this knowledge about tables and probability in order to evaluate hypotheses. We came up with a null hypothesis. We simulated under that null hypothesis to get a null distribution. What is a p-value? The p-value is the chance under the null hypothesis that the test statistic is equal to the value that was observed in the data. That's why we use the observation. Or even further in the direction of the alternative. So if the alternative hypothesis was that this coin had fewer heads than tails, you'd look that way. When the p-value is high, the evidence is consistent with the null, and you cannot really choose between the null and the alternative. But when the p-value is low, there's more evidence for the alternative. If it's really low, you can reject the null hypothesis entirely and think that the alternative hypothesis is a better description of the world. Okay. What's the p-value cutoff? It is your personal threshold for deciding whether or not you think the p-value is small enough for you to reject the null hypothesis. Typical values are 5% or 1%. It is also an error probability. Approximately the chance that the test will conclude the alternative, even though the null hypothesis is true. So if you happen to live in a world, so when you're running a hypothesis test, you don't know whether you live in a world where the null is true or the alternative is true. But let's say the null is true. Your p-value cutoff is the percent of the time that when you run a hypothesis test, you will reject the null hypothesis, even though it was true all along. That's why it's called an error probability. You get to choose the cutoff, so you get to decide how often you're willing to tolerate such an error. The cutoff does not depend on the data, and often you will choose it before the data are even collected, before you try to run your experiment. Factors affecting the p-value. We kind of went through these, but here's like a question you might see. Which of the following does the p-value depend on? The null hypothesis, the alternative hypothesis, the choice of the test statistic, the data in the sample, the p-value cutoff. What do you think? Talk to the person next to you. Come on. Okay. The null hypothesis determines the shape of the null distribution. Yeah. This can definitely affect the p-value, because this determines the null distribution, and you're using that. Alternative hypothesis matters, actually, yeah, because it tells you which way to look. You look left or you look right. The choice of the test statistic matters because this is important to your simulation. You use the test statistic in your simulation. The data in the sample, yes, that does matter. That tells you where to start when you compute the area of the tail. The p-value cutoff doesn't change the p-value. It's what you compare. It's how you interpret the p-value. The p-value is what it is. The cutoff tells you whether you think it's small enough, but it doesn't change the p-value. So I would have said all except the cutoff for this. Well, that was fun. See you at 7 o'clock.